Hello and welcome. Today we're going to be deriving Laplace's equation. And the real key concept here is that it's all about equilibria. So let's start with the equation we're going to do. So we're really going to focus on two spatial dimensions. Okay, so we're going to have an x and a y, right? And then, of course, we're also going to have time. We're going to start with time, but of course, we're going to eventually approach this from the perspective of equilibria. So the approach of an asymptotic behavior as time gets really, really large. We're talking about two spatial dimensions, and we're also going to focus on the heat equation or the diffusion equation. They're the same equation. Depending on your perspective on physical units, you can interpret them both ways. Okay, so heat and diffusion. So, of course, with all of this, we're going to start with, we always start with a test set. In this case, we're going to start with a test set R. Okay, actually, let's not do R. Let's use a different variable. We'll say W. Okay, so in this case, we have x, and then we have y, like so, and then we have some set w right there, and we also have the boundary of w. Okay, so the outside edge of w, which we'll put in blue there. Okay. So as always, we're going to say u is some amount of stuff, or maybe it's the heat energy or the amount of mass in W as a function of time. And it's going to be, we'll think of this in terms of the diffusion equation, where we're talking about the conservation of mass, in which case we do a double integral over W of the density dA. Okay, so there is the density. Okay, so with that density, the next thing, of course, we want to do is, and we'll just abbreviate that to W. It doesn't really matter. I don't want to use so many letters in my notation. We can now take the time derivative, and we know from conservation, what we have here is that this has to equal the negative flux out plus any sources. Okay, so let's talk about what those terms are. Typically, we talk about the flux out. We're going to be talking about some normal vector, and I'll give a few of these normal vectors hanging around our boundary of W. In which case we're going to say this is actually negative the integral on the boundary of W times the flux rule dotted with n ds, where ds is a small area, or sorry, not a small length segment on the boundary. And then we also have a double integral over the interior of W of all sources, and I'll call those sources by a term called R dA. All right, so for diffusion or the heat equation, we know that the flux rule, which is now a vector field, is going to be equal to negative d times the gradient of u. We can write this as follows: ux, uy. Okay, that's our gradient vector. All right, and then use the divergence theorem. And then we know that if I take the flux field, or the flux integral that we have here, we can rewrite that as the integral I'll substitute this in. What we have here now is going to be a negative d grad. We're starting with the negative, so I'll just make that a plus there. That should do it. And then we have a grad u ds. But then we're going to use the divergence theorem here and turn that into a double integral over the interior of the set. I'll bring the d constant out, and then we're going to have grad, the divergence of our gradient vector, dA. And now there's a new piece of notation we're going to learn, which is we're going to have del squared u dA. So it should be noted that del squared is actually del dot del u, or grad dot grad u. We're going to call that grad u squared. And this right here, that's what we call the Laplacian. Okay, so the Laplacian is defined in both 2 dimensions, 3 dimensions, or any number of dimensions. And is a very common operator. It's so common that it's given its own symbol, special symbol, because it's used so often. Okay, so we're here. Now I'll move up to give myself a little bit more space. We can put that all back together, and we have this. So we're on W, and we're integrating over all of W. Okay, so we have this equation, and then we make the insight, of course, that W is arbitrary. So we can remove the integral, in which case we have the PDE. Okay, so there's our PDE. So we've derived our PDE. And now, before we solve this, so obviously u is going to be a function of x, y, and t in this particular case, right? However, before we try to solve this completely, what we're going to really look for is now look for equilibrium solutions. We're going to look for equilibrium solutions. And those equilibrium solutions are going to be, of course, when the partial derivative of time is equal to 0. All right, so we're going to go to the next page, and I'll talk about these equilibria. Okay, so what we have here is this equation here. All right, so I can rearrange, and we have the Laplacian of u is equal to r over d, okay? And we also have, we could be on a domain W, okay? So it could be this test set we talked about before or some other set, it doesn't matter. We have W here. And there's my x and there's my y there. And then of course we also have that boundary of W. Okay, so we're looking at some open set that we're interested in studying. We'll just say it's connected to make it simple. So this equation here, when r is not equal to 0, they call it Poisson's equation. Okay, when r is equal to 0, we call it Laplace's equation. So in this video, we're going to talk more about Laplace's equation. So that's Laplace's equation right there. Okay, so it's a PDE problem. And we should probably study more about this Laplacian. We said it was grad dot grad u. We can write that as follows, and we end up getting uxx plus uyy is equal to 0. So that's probably the more explicit way of writing Laplace's. Okay, so it's really important to know that this equation shows up, this PDE, it arises in the heat equation, diffusion, electrostatics, and dynamics. You see Laplace's equation all over the place, not for dynamics, but rather for electrostatics. If you see the Laplacian all over the place, so maybe I'll erase the dynamics part. Obviously, if you have a time variable in there, the Laplacian will be equal other things. But in Laplace's is basically an equilibrium heat or diffusion equation. And of course it shows up in multiple spatial dimensions. So 2D, 3D, and so on. Okay, so we want to talk about other things. So what comes with this is what we need. We actually have to need, and we needed to define the boundary conditions. So there's two types. There's what they call Dirichlet, and Dirichlet boundary conditions specify u where x comma y is on some boundary of our domain, and it's equal to some pre-specified function. And the second type of boundary condition is called a Neumann boundary condition. And it is a flux condition. So it's going to be of the following form. We have n boundary of W. That's the outward normal. And so I'll even write that outward normal on here. We can have, there's an NW, partial W. I'll just abbreviate it as N. You get the idea. N could be just pointing everywhere, always perpendicular to the tangent of the boundary curve. Okay, so we have that outward normal. What we say is, we say that the gradient vector, the gradient of U, dotted with N boundary normal, evaluated on the boundary, and we say it's equal to some specified function. So here we're saying that the flux condition, it's specifying a specific flux. All right, let's get a little bit more into the solution. So I really want to talk about more. I'm going to talk about the Dirichlet boundary a little bit, and we can wrap this video up. So the Dirichlet, or what they call a fixed temp, a fixed value condition. So if I were to draw this in 3 dimensions, so you have u there, you have x there, and you have y there, and then we have our w set here. The Dirichlet says that essentially u, when evaluated on the boundary, is equal to some function. And so what you're saying basically is that you have, we'll call this function w, and I'll write, or sorry, f, and I'll write it in blue. You're basically saying that around the boundary, so at every point x comma y, there's a value on it. Same here. At every point, there's the height of that blue curve represents the value of the function u, like so. Right, so the question that Laplace's equation poses the question can I find a function u of x comma y such that u on the boundary equals f and grad squared u is equal to 0. So is there some function, some sort of surface that connects all these points? On the boundary like that. So there is u of x comma y. So that's the best way to think about it. So what you can think of basically is the boundary condition. The boundary condition f is basically the given, or the input. And your job is to find u on the interior. It's the input, and of course by the input I mean that it's the input is given on the boundary. Okay? All right. So it turns out that of course the solutions always exist, provided that the function on your boundary is well behaved enough, and they're unique. And they also have lots of special properties. We won't get into all the special properties. We won't talk about them in this video because there's too many to list right here. What we can say though is that these solutions are special. They give them a special name. They call u a harmonic function. They call it a harmonic function. So that is a very special name, and that means it solves Laplace's equation. Okay. And by a special name, it owes to the fact that it's so prevalent all over physics and mathematics. Harmonic functions are very special. They represent, again, these sort of equilibrium concepts, these balance points between lots of different forces and tensions. And they are sort of harmonious, if you will. Okay, so I want to talk a little bit more about that other boundary condition, so Neumann boundary conditions. All you're doing is saying, you're basically specifying the directional derivative at the boundary. So just like before, you can put yourself in 3 dimensions, and you have some set W, and you have some boundary. But rather than setting the height W, you're setting the slope of the surface. So you're saying that, now I don't know what the height is, but, and this is hard to draw, but you're rather looking at every point on the thing and saying that the slope of the curve, slope of the surface as it leaves the boundary, right as it crosses the boundary, is specific. And again, it's difficult to draw. I'm trying to draw that as best as I can, and basically you're saying that the gradient of u dotted with the normal, and the normal I'll draw in blue like that, n, okay, when you evaluate on the boundary, is equal to a specified thing. So you know what the slope is of the surface as it's on that boundary. Okay, so that what you want to try to find is there a solution that does the best job that will find will have the slope on the boundary that we specify, but will also solve grad squared u is equal to 0. Also a harmonic function, it's just a different type of boundary condition. It turns out that these are unique up to an additive constant. And there's another thing that we have to specify here. Not all g values are allowed. Not all g, I shouldn't say values, I should say functions. It has to be subject to a special condition. And again, the idea here is that u must be an equilibrium. So what I mean by that is that, let's go back to the heat or the diffusion PDE. So we have that PDE, and we integrate over W dA. And we know that that means that du dt is equal to 0, and that's the equilibrium. But we also know that has to be equal to that flux integral at the boundary. Well, that's g right there. What that means, though, is we can see clearly that it must be that g, when you integrate it around the boundary, has to be equal to 0. So what we're saying here is only special g functions are allowed. So there's some restrictions. So it's not as flexible as the Dirichlet boundary condition. However, in many cases, what you know that what you're going to be doing is you're going to be giving a flux condition, and because you're in equilibrium, it must mean that basically the net flux must be zero. So of course you're looking for an equilibrium. If you're studying a Neumann boundary condition, you're doing it subject to this idea that the flux has to be net zero. So it's a natural condition to have, but it's one of those things you have to be mindful of. Not every function you can use there, only special ones. And so that turns out to be actually a really important property of Laplace's solutions, is that they do have zero net flux. In fact, you could even say that is the definition of what Laplace's equations are, that they all have zero net flux out their boundaries. We'll talk more about some of those special properties of Laplace's solutions in later videos. I wanted here just to give a high-level presentation of what the big features are, what the big terms, all the terminology is, and the different types of problems that show up, and of course how they all relate back to conservation and flux. So we'll leave here, and we'll come back in the next video and start talking about actually finding solutions. All right, thank you very much.